Welcome to this presentation, an introduction to programmable logic controllers. This lecture will start at the very basic level. It does not assume that you have any prior knowledge of programmable logic controllers. However, there are some sections of this presentation that will require that you have a fundamental understanding of basic electricity. If your background is in computer science, this presentation will quickly enter into territory that you are already familiar with. After all, PLCs are computers, and logic is, well, logic. I have attempted to make this presentation as generic as possible. This presentation was recorded to accompany a training manual written for a specific family of processors. However, this presentation can be used as a standalone lecture, keeping in mind that the examples are from a specific family of processors. A brief bit of history is needed here to build a background for some of the terminology and the symbols that we use when we program programmable logic controllers. This is an illustration of one of the original relays invented by Edward Davy in the 1800s for the telegraph system. Without going into a lot of detail explaining line losses of signal over long runs of telegraph wire, it is sufficient to say that to prevent the loss of the telegraph signal over these great distances, they installed relay stations to restore the signal level. So the original relay was a device for relaying the contact closures for the telegraph key at intervals along the telegraph wires as they traveled across the country from the East Coast to the West Coast and back. Once the relay became known as a device, it was not long before engineers realized that there were other applications for contact relays. If you could use a relay to relay a contact closure into an isolated circuit in order to restore the voltage levels, then you could also use a relay to relay a contact closure into an entirely different circuit with an entirely different voltage type and level. In other words, using a switch that supplies, say, 24 volts DC to the coil, so it's a 24 volt DC circuit, but have the contacts switching 480 volts AC and switching heavier contacts to handle much higher currents. So you're basically controlling a high voltage, high current device with a low voltage, low current device. The most dominant feature of a relay is the coil. The coil is also the load in the switching circuit. The coil is wound around a pole piece. The pole piece is a rod of ferromagnetic material. The coil and the pole piece constitute an electromagnet. The object of the electromagnet's affection is the armature, which is another piece of ferromagnetic material that is suspended near one end of the coil by a spring that would oppose the magnetic field. Attached to the armature is a moving contact. The moving contact travel is restricted in each direction by stationary contacts. When current flows through the coil, the armature is drawn to the pole piece of the coil against the tension of the spring. As the armature travels towards the coil, the moving contact travels as well, coming to rest against a stationary contact. When the circuit containing the coil is opened and the coil de-energized, that is turned off, the magnetic field collapses and the spring tension is now the dominant force, and the armature and the moving contacts attached to it move away from the pole piece. The movement away from the coil is limited by a stationary contact, and the movement towards the coil is limited by a stationary contact. So, as power is alternately applied to the coil, the moving contact makes contact with the two stationary contacts. One contact when the relay is de-energized, and the other when the coil is energized. Let's look at this relay in a diagram form. Again, you have a coil wound around a ferromagnetic pole piece, a ferromagnetic armature that is attracted to the pole piece, a spring that opposes the armature as it moves towards the coil, and a set of moving contacts that travel with the armature and make contacts with a limit of travel. The normally open contacts limit the energized travel, and the normally closed contacts limit the de-energized travel. When this coil is energized, the resulting magnetic field attracts the armature towards the pole piece of the coil, overcoming the spring tension to open one set of switch contacts and then closes another set of contacts as the armature reaches the end of travel. As long as the coil remains energized, these contacts are held closed. When the coil is de-energized, the spring tension opens this set of switch contacts, and consequently at the end of the spring travel closes another set of contacts. As this presentation continues, it will become apparent why a short discussion on relays will bring a more clear understanding of programmable logic controllers. The programming language used to create or write programs for a PLC, programmable logic controller, is based upon relay circuit symbols. The original relay control panels use relays for the logic, and the most common programming language today for PLCs is ladder logic. This language evolved from the symbols on the electrical prints. Let's put this relay into an application. You could say that there are three public interfaces to this circuit. The first one, the single pole, single throw switch that is operated by the operator. The second, a red indicator that is seen by the operator. And the third one, a green indicator that is also seen by the operator. So the operator has access to control the switch, and then a red and a green LED or indicator indicate to the operator the conditions in the circuit. The power supply, the actual relay, and the DC power supply would not be visible to the operator. The circuit that controls the relay is powered by alternating current. A single pole, single throw switch is used to both complete the circuit, to energize the relay coil, as well as to open the circuit to de-energize the coil. The coil is wound around a pole piece of ferromagnetic material. As current flows through the coil, a magnetic field results, and this field is intensified by the pole piece that the coil is wound around. The resulting magnetic field from the pole piece magnetizes a piece of magnetic material that is attached to the moving contacts, the armature. As this piece of material becomes magnetized, the two magnets are attracted to each other. The spring yields to the magnetic force, and the two magnets are drawn together. The normal state for a relay is de-energized. Hence, the upper set of contacts are normally closed, and the lower set of contacts are normally open. With a single pole, single throw switch in the open position as shown here, the relay is in the normal state, and the normally closed contacts complete the circuit from the DC source of power to energize the load, which is a red indicator. When the single pole, single throw switch is closed, the current flows through the relay coil, generating a magnetic field, pulling the armature and the contacts attached to it. When the normally open contacts close, they close the circuit for the DC source of power to energize a different load, the green indicator. You could say that this relay relays the state of the single pole, single throw switch in the AC circuit to the normally open contacts in the DC circuit. The normally open contact of the relay matches the state of the single pole, single throw switch. I've never seen a relay without a normally open set of contacts, but I have seen many without normally closed contacts. Normally closed contacts were added to allow using the off state of the relay to control other actions. The components of a relay that are of interest to the control system are the coil, the normally closed contacts, and the normally open contacts. This circuit has all of the basic components of an industrial control system: an input device, the switch, output devices, the red and green LEDs, and the power sources to control the output devices by means of the input device. Looking at this relay in diagram form again, here are the symbols that are used to represent the relay and its contacts in a relay electrical circuit. A relay's contacts are used in electrical circuits to determine the state of the relay coil, de-energized or energized. In most instances, there is a set of conditions that must be met to energize the relay coil. Instead of a single switch to control the relay, there is more than one contact that must be closed to energize the relay coil. The state of the relay coil then becomes a collective representation of the true or false condition of the set of individual conditions that energize or de-energize the relay. The normally closed contact is used to determine if the relay is de-energized, and the normally open set of contacts are used to determine if the relay is energized, or you could say that the normally open set of contacts are used to determine if the set of conditions that energize the relay is a true statement, whereas the normally closed contacts are used to determine that the collective conditions are not met or false. A normally closed contact is true if the relay is de-energized, and false if the relay is energized. A normally open contact is true if the relay is energized, and false if the relay is de-energized. If this is not clear to you yet, hang in there. It will become clear as we continue. Let's look at this example. Look at the bottom rung in this relay circuit. You have 3 limit switches labeled shuttle home, lift home, transfer home. They are the permissives or conditions that determine if the all-home relay 1CR is energized or de-energized. So the coil, the state of the coil 1CR, becomes a collective representation of those 3 limit switches. If those 3 limit switches are closed, then that rung is true. You have continuity. 1CR energizes, and all normally open contacts associated with 1CR also close. And at some point, if the other conditions become met in the upper rung, then OK to start relay 2CR becomes a collective representation of those 4 conditions, one of which, 1CR-1, is a collective representation of all 3 limit switches. Well, you're probably saying, why don't you just take those 3 limit switches and move them up in place of 1CR-1? That would work if this were the entire circuit. But we may need to use other normally open or normally closed contacts from the all-home relay 1CR in other areas of our circuit. In that case, we wouldn't be able to use those 3 limit switches in all those different locations. So instead, we use those 3 limit switches as the permissive or conditions for 1CR, and then 1CR becomes the collective representation of the home limit switches every place else in logic that we need it. Take a few moments and review this relay circuit. The object of the circuit is to control a cylinder with a double solenoid valve. The heart of this circuit is the control relay 1CR. In an actual relay control circuit, each set of contacts have a unique identification. Physically, the contacts in the coil are one device, but in the actual circuit, the coil and the contacts that are controlled by the coil can be separated onto completely separate sheets of the drawing set. For this reason, each set of contacts may be individually identified by the parent coil ID and sequentially numbered for each set of contacts belonging to the parent coil. As illustrated here, the control relay 1CR is the parent ID, and all contacts controlled by that coil are identified by 1CR-1, sequentially 1CR-2, etc. Normally, there would be a cross-reference immediately to the right of the symbol for the coil that would provide the sheet and line number for each contact usage from this parent relay, 1CR. In the normal state, push button 1 is not pressed. Contact relay 1 is de-energized. Normally open contact 1CR-1 is false. Solenoid 1 is de-energized, and 1CR-2 is true. Solenoid 2 is energized because 1CR-2 is normally closed and the relay 1CR is in the normal state. In this circuit, there is only one condition or permissive in each rung that determines whether the load is energized or not. Remember that the contacts 1CR-1 and 1CR-2 are mechanically slave to the motion caused by the relay coil energizing and de-energizing. In the normal state, are any devices energized? Are any contacts true? Are any contacts false? When push button 1 is depressed, are any devices energized? Are any contacts true? Are any contacts false? One CR-1 is true if 1CR is on or energized. 1CR-2 is true if 1CR is off or de-energized. Take a few moments and review another relay circuit. The object of this circuit is to control the state of contact relay 1, 1CR. This circuit has more than one condition or more than one permissive to determine whether or not the load, which is the relay coil, will or will not be energized. If a permissive or condition is in series with other conditions, such as normally open 1 PE and normally closed 2 PE, they are said to be ANDed. If the permissives or conditions are in parallel with other conditions, such as normally closed 2 PE and normally open 1 CR-1, they are said to be ORed. In this circuit, to energize the relay coil, you need to complete a path for current flow from one end of the circuit to the other end. The circuit must be completed through photo I1 normally open contact, that's 1 PE normally open contact, and photo I number 2 normally closed contact, 2 PE. But once the relay is energized, the circuit can complete through normally open contact 1 CR-1 from the relay itself. Therefore, photo I2 normally closed contact could go false and the relay will remain energized because the relay's normally open contact 1 CR-1 has sealed in the temporary condition of normally closed 2 PE. The only method of de-energizing this relay is when photo I1 normally open contact, that's 1 PE normally open contact, goes false, thereby dropping out 1 CR coil, which sends 1 CR-1 back to the normally open state. The logical statement of this rung of relay logic would be stated in one of two ways. You could say if photo I1 and not photo I2, which means if photo I1 is energized or on and photo I2 is not on, hence the if photo I1 and not photo I2, And then we have an OR circuit here. So it would be repeated once again, if photo I1 and not photo I2, or if photo I1 and 1CR-1, then let contact relay 1 equal on. Or another way to state this would be with ones and zeros, which is more common to a PLC. If photo I1 equals 1 and photo I2 equals 0, or if photo I1 equals 1 and 1CR-1 equals 1, then let contact relay 1 equal 1, or on. With 1CR-1 branched around not 2PE, 1CR is able to retain a specific condition regarding photo I1 and a temporary state of photo I2. What can 1CR remember about the state of 2PE once 1CR is energized? That's correct. Once 1CR is energized, no matter what 2PE does, 1CR indicates that 2PE was not on. It was in the not state, normally closed state, in other words de-energized, when 1PE came on and completed the circuit to turn on 1CR, which closed 1CR-1 to bypass not 2PE or normally closed 2PE. What will happen if 2PE comes on after 1CR is on? What will happen if 2PE becomes on, not true, but becomes on after 1CR is on? Nothing. Once 1CR is energized, no matter what 2PE does, it does not affect 1CR after the initial condition of 1PE and not 2PE. Once that logic is true, 1PE and not 2PE, 2PE can go on and off and it's not going to affect 1CR. What is the only condition that will de-energize 1CR once it's been energized? That's right, not 1PE, meaning that 1PE has to go false or 1PE has to de-energize. Remember, normally open contact is open when the object of that contact is off or 0. Okay, so 1PE is true only when 1PE is energized. Let's take this circuit that we've been looking at and make one modification to it. Let's move the normally open contact, 1CR-1, from being ORed with the normally closed contact from photo I2, 2PE, to being ORed with the normally open contact from photo I1, 1PE. How does that affect the logic of the permissives or the conditions to energize or de-energize the contact relay 1, 1CR? What can 1CR remember about the state of 1PE and 2PE? That 1PE was on when 2PE went to the off condition. What will happen if 2PE changes to the on state? Now, I didn't say what happens if 2PE normally closed contact goes true. I said if the photo I, 2PE, goes to the on state when 1CR is energized. What will happen if 2PE comes on after 1CR is energized? That's correct. 1CR will de-energize as long as 2PE is on. Because there are no ORed conditions now around normally closed 2PE, 1CR cannot be on, cannot be energized at any time that 2PE is not on. Because if 2PE is on, then that normally closed contact will be open, or you could say that not 2PE is false. It's not 2PE when 2PE equals 1. What is the only condition that will de-energize 1CR once 1CR has been energized? keep in mind that 1CR-1 is closed anytime 1CR is energized, and 1CR1 bypasses 1PE normally open. So what is the only way to de-energize 1CR once it's energized? That's correct. 2PE photo Y comes on. On is not the normal condition, so the normally closed is no longer closed. Back in the day, there was a relay control panel. And this relay control panel had hundreds, maybe even thousands of relays, and more insulated wire than a grown man and two boys could carry. The brown rectangles here in this illustration each represent a relay. If you remember from an earlier illustration, we mentioned that an industrial control system has input devices and output devices, and that the output devices are controlled by the states of the input devices. To keep our illustration simple, we will connect all of the input devices, that is toggle switches, limit switches, photo eyes, etc., to a vertical terminal strip on the left end of the control panel, and then these terminal strips go to the coils on the column of yellow relays. And then we will connect all of our output devices, solenoids, motor starters, and contactors, to a vertical terminal strip on the right end of this control panel here. And the contacts from the vertical column of yellow relays are connected to those terminal strips. So in other words, the contacts from the yellow relays on the right are connected to the terminal strips to control, switch on and off the output devices. The column of yellow relays on the left end of the control panel are unique in that their coil voltages match whatever the field voltage is used for the various input devices. So some input devices are 5 volts, some are 24 volts DC, some are 115 volts AC. So you have to have a relay coil. In other words, the yellow relays on the left side are the electrical interface between the input devices and the control panel. So each of those yellow relays converts the on and off state of the input device to an open or closed contact for use by the brown relays. The brown relays will all be one coil voltage, 115 volts AC or 24 volts DC. The vertical column of yellow relays on the right will have the same coil voltage as the brown relays on the control panel, either 115 volts AC or 24 volts DC. However, their contacts will be capable of handling whatever is needed in amperage for the output devices, as well as they will be switching whatever voltage is required by the output device. So you might have input devices that are 24 volts DC, panel relays, the brown ones, that are 115 volts AC, and then your output devices might be 240 volts, 480 volts, 24 volts. So the two vertical columns of yellow relays are the electrical interface between the input devices and the logical panel, and between the logical panel and the output. I mentioned earlier in this presentation that we would replace these relay coils with computer memory as the first step in our transition from relays to a programmable controller. To make this illustration a more simple transition, let's rotate the relay panel to more closely resemble an array of relays 16 coils wide, and increase the quantity of relays to match a typical computer memory size, in this case 8K of RAM, random access memory. We have relays 0 through 15 in each row, and then we have 8,192 rows, or 8K of rows, starting with row 0 and ending with row 8,191. Since all memory locations start with 0, you always subtract 1 from the quantity to get the highest address. So if there's 8,192 rows, and you start with row 0, the last row will be 8,191. Let's take a closer look at one element from this array of relays. Each element of this array has a coil that is on or off, 1 or 0. If we want to allow current to flow in another circuit, if a particular relay coil is on, we use a normally open contact, and if we want to allow current to flow in another circuit if a particular relay is off, we use a normally closed contact. You could say that if you want to query or question a particular relay coil to see if it's in the on state, you would use a normally open contact. If you want to query or question a particular coil to see if it's in the off state, you would use a normally closed contact. The use of these contacts to check the state of the relays is the basis for all relay logic. One major disadvantage to using relays for logical control is that each contact can only be used once in a logical statement. If you need to check the state of a relay in more than one logical statement, you need to add more sets of contacts to the relay. However, keep in mind that there's a limit to how many contact blocks you can add to a relay. Each contact block has its own spring, and a relay coil only has so much force to overcome these springs, and each contact block adds more springs that have to be overcome.